Is the screen visible to you all?
Yes, sir.
Okay. So today we will be discussing about a very important topic called deep learning, uh, which is basically the boom why the learning has again come into picture. So if you look at the landscape of how we proceed from artificial intelligence into deep learning, is that initially by uh, McCloskey and others who thought, I mean, the dream of, obviously the dream of Turing, as that machine can think, give birth or give the genesis of AI, where we use planning, different kind of search, heuristic techniques in order to make algorithms so that it enacts the thinking of human being. Then we saw that we have a large proliferation of data and all, and then we go for learning some of the facts that human can learn, when we can imitate that learning through the concept of machine learning, as we have seen throughout the course. And gradually, when we have higher and higher scope of data in the era of big data, we can just emulate human being, just like the emulate the vision perspective of human being, emulate the sequence of operating perspectives of human being. Like I can, from the history, I can predict something very well. I can relate something very well. So it just have another dimension to learning due to the large enough data that we have to train. This gives rise to the field of deep learning, and this gives rise to the importance of deep learning in solving many practical problems that could have not been thought about or could have not been touched in earlier sense. If you remember that the whole deep learning concept has been driven from the concept of artificial neural network, and it's an extension of that. So if you remember that, suppose I want to classify, as the classification is one of our traditional tasks in learning. Suppose I want to classify this, and this is the target function that I would like to learn. And you can see that, I mean, you can figure out that in terms of neural networks. So if these x1 and x2 attributes are my input attributes, then you can easily understand that through neural networks I can have certain kinds of nodes where this is the bias, that is 1 with the weight w0. I hope you remember. Then again I pass it through different nodes, and finally give it as a feed forward neural network, construct a feed forward neural network. So if you now try to think back and realize this neural network decision making over the whole space of points, what it does, it's a classifier, right? So it tries to classify with respect to different boundaries that it could draw, right? I mean, I, through the different stacking of the layers, I can draw such kind of a boundary, and I can segregate the points. Yes or no? Agreed? This is the typical artificial neural network thing that we started off with, right?
Yes, sir.
Now, if you look more closely, that there is a relation. So if you try to remember in artificial neural network, when we have realized and then we went to realize XOR, you will see that we have higher depth, right? We have higher depth in neural network to realize that, which means that we can view. So to let me make the elementary unit as one of the elementary unit was the summation unit, where all the inputs come in from x1 to, let's say, d dimensional xt, and this is the mandatory one input, and then it passes through, which is called a logit or logistic unit, theta. So this sum passes to theta, and we get the heuristic as theta of s. And sometimes we take this function as a sigmoid function, as you know that the sigmoid nature is like this, to make it continuous, so that when we back propagate, we can make a double derivative out of it and can adjust the weights. Now, again, from the genesis perspective, why neural networks need higher number of data? Because you can see here the number of parameters now you need to estimate are much higher. So obviously you are learning with respect to data, you are learning from the input output levels. So if the data is not very much in your hand, then all these weights cannot be equally well trained. So that's why in the higher the depth in neural network, the more the data we want to train. And due to the current age, having a proliferation of such data make neural networks more realizable. So you use such kind of deep networks, which is the deep learning aspect of it. However, you can also notice that what does this depth brings into? This depth in a way can bring such kind of different fine-tuned classification boundaries into this figure, right? I mean, if I go into more depth, you classify in one dimension, then the other depth classifies in other dimension, the third depth classifies in third dimension, and you get such kind of a pores in your Euclidean higher dimension space, where these pores are your positive classes, the rest are the negative classes. So depending on the depth, you can extract out more finer, or you can have a multi-dimensional such kind of target function, which is not basically linearly separable. You can do all that. However, there is a very fine aspect that we often miss in artificial neural network, in feed-forward neural network, is this, that if you see, every layer is basically, in feed-forward neural network, takes the input from every other previous layer values. Here you see every layer takes the input from every other previous layer. And that's the artificial neural network fundamentally what it is. But you see what we miss by that. So suppose I have this layer L-1 feeding to layer L, and another neuron also takes all the inputs from this. So what we miss here is the spatial information difference between them. So what does this will compute? This will compute a logistic function over the summation of Wi into xi. This will also compute a logistic function over the summation of some Wi dash into xi, right? I am assuming these as the xi's, and these are Wi dash and these are Wi's. So you can see that what difference do we make here? We may make in an Euclidean space, maybe our plane is this way or that way, right? If it is a two-dimensional, I could say that the separator plane is this way or that way, depending on the change in Wi dash or Wi that I could make it. However, we do not look into the spatial information is totally lost, because we just push every information in every possible node to reason about it, right? Why this is a problem? Because now you see, suppose you are looking at an image, it has many different zones to look at into it. Just vis-a-vis compare with our vision. Do we take everything together and process similarly? Then how do we identify there is a bus, there is a pedestrian, there is a crossing, there are cars, some cars are moving, some cars are not moving. So in order to incorporate that particular attribute into machine, to understand that attribute into machine, we need some kind of feature extraction, right? That means that not the overall thing that was given to me is together faded into one unit, or maybe together faded into different unit to classify. This is not what I look for. Rather, I look for this in a zone by zone basis. Maybe some zones may overlap, and I would like to take decision based on the composition of features that I get out from this. Try to understand this very carefully. That hence you can see that suppose there is an image, it is nothing but pixel values at each positions. So I have pixel value x1, x2, x3, x4, x5, x6, x7, x8, x9 up to x12, x13 up to x16. This is a 4x4 image of a pixel, right? Now when I feed that to a network, what I would like to do, rather I look into positional aspects of it, not the full image, and try to extract out features, high level features from each of them. Suppose one neuron extracts this, one neuron extracts this, one neuron extracts this, Then we can compose these two. We can compose first, third, not all of them. Then we can compose 1 and 2 and give an output, right? So you can see here that why the depth, that is the number of neurons in a layer, that is sorry, the breadth, that is we call the breadth of each layer, and why the depth both matters. The breadth is basically how many features we are distinguishing and trying to reason about from them. Or in the visionary system, if you try to analyze and give an analogy with the human, how many different zones we are looking and trying to arrive at a decision when we look at a open road. Then gradually through the depth, when we move on, we try to compose these features, the salient among them, and try to build up over this, right? So this is how we can embed little bit of human kind of vision into the neural network, where there are features, extractions, which may be hierarchical. Meaning that, let's say at level 1, I extract the edges of the image. At level 2, I extract the boundaries of separate images. At level 3, I compose them and extract objects. At level 4, I see associations of objects. So this way I move on when I move on to the depth wise, and then finally get a perception of the image at the output, right? The philosophical fact is clear to you. So this is
Yes,
in a
sir.
way, yeah, this is in a way very important, because image is such a thing, or maybe in many things, image is one of the examples that I am showing. That suppose you want to identify 5. Now, if you take the whole image and pass it to different neuron, you will only can identify certain orientations of 5. But your 5 may be like this, right? Your 5 can also be like this. Your 5 can also be like this. Why do we need feature to extract? Because instead of taking the whole image as it is, if we could have taken the bendings of this part as a feature, the straightening of this part as a feature, then you see this bending and straightening will match in every other parts as well. So if we could push down to some nodes and then could manipulate and compose it hierarchically to define the object and their associations, then maybe different orientations, occlusions, the brightness, or maybe the some kind of I would say the shades, all this we can tackle, right? So because when learning, what I will try to learn now is not a particular orientations of image, but features which can relate together and can form this 5 in a different orientation. So we are at a position in order to understand an object from the input side by extracting features. Maybe the features could be inside it also, by extracting features and then by composing them and moving on. So this Holy Grail has a very significant contribution to deep learning, which we call as a convolutional neural network. And this is the de facto in image identification. We will show you one by one the steps of this. So let me again draw a very basic diagram to understand what the feature is. Just give me some time to draw it. suppose you are writing an X, right? So this is the I would say the enlarged pixel wise value of how do I, when I see an X, suppose these cells are darkened. I mean, my white color is actually the darkening cells. Now somebody could have drawn this X thing in a, okay, now somebody may have drawn it. So this is also an X and this is also an X, right? I hope you can understand that these pixels are -1 and these pixels are +1. I mean, in RGB, in the grayscale, you may say that these pixels are black, so 0, and these pixels are white, maybe, so 255. So see, what does it mean that this X, I wrote it perfectly. This X, I just do a tilted thing, handwritten images. Now, if you look at the feature-wise comparison, suppose I took this as one of my feature, this as one of my feature, this as one of my feature, this and this. Now the similar thing you can see, I can observe this as one of my feature, 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 and this as one of my feature. Right? I mean, this is boundary. So, I mean, if you do not do it feature by feature, rather give the whole input image, I will just try to look for an X as it is, not the tilted orientation. Maybe someone can write it this way, maybe someone can write it this way, so the pixel values, the darkening pixel values may differ. So you can see now my job is easier because I will try to match this, I will try to match this. Agreed? I will try to match this. And then I will say that these two are X's. So the positioning orientation I can live away with if my visionary skills I can apply, not looking at overall as a zone, but looking at a part of it as a subzone and then deciding. So therefore, what I need to do now to draw a neural network or to build a neural network is to figure out such things, what the extracted unit would take forward, which value the extracted unit should take forward. So depending on this X, you can see I took these set of features and then try to figure out certain nodes out of these features and then push it forward, right? Because these features I will just extract out and then my nodes go on forward and deciding on a neural network structure. So I need to know which block, suppose this is the block that contains these features, which is matching with this block that contains similar feature that I have extracted, right? This, what we will do is, in mathematics we call a convolution operation. How do we do that? Suppose this, I build a kernel 3 cross 3. This is 1, 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 this is -1, -1, -1, -1. Now, how does this kernel, if this is a 3 cross 3 matrix and I keep on scanning 3 cross 3 zones overlapping wise in this figure everywhere. Now, this zone, if I multiply 1 with this one, minus 1 with this minus 1, and then take a sum, this zone will give me 9 as output. No other zone will give me this much number as an output. Do you agree? Because my blank cells are minus 1, my filled up cells are 1. If I move this particular block of matrix and try to take row and column wise multiplication of the numbers and take a summation, only the zone that I highlighted here will give me the maximum value as 9. No other zone will give me such a maximum value. Do you agree?
Yes, sir. Agreed.
Here also in this figure, the similarly some zone will keep me maximum this 9, the other zone will not. So what do we are getting it? We are getting a particular feature which is understandable through a realization of a kernel, right? What is this feature? I mean, if a human being has to tell what is this feature, this is, I would like to understand the center of X. This is the feature. I would like to understand the center of X. And upon convoluting, which gives me the max value, I will determine that zone as the center of X, right? So this way we can easily understand an image even if it is differently located. I can understand the center. Similarly, I can design another kernel, 2 cross 2 kernel, which could have -1, -1, 1 and 1, which will identify this thing perfectly. Right? It will also identify this one as the perfect fit. No issue, but both will be my feature. But the good part of this is that even if somebody wrote a little tilted X, then also I can understand that this is my center. I hope you can agree now by this. Right?
Yes, sir.
So to be more formal, the convolutional operation, what it does is, given a metric like structure, suppose I have a 5 cross 5 matrix, I just convolute. Suppose this is my convolutional operation. One of the operation is multiplying sum, that is my defined operation. You could define any other operation. Suppose this matrix has 5, 3, 9, 4, 0, -1, -4, 2, 0, 5. So this is an image matrix. And suppose this kernel, let us take the same kernel, 1, 1, 1, 1, -1, -1, -1, 1, -1. Then what I will do, I will first do this operation of this kernel over this block, and in the final output, here I will write that value. The second thing, I will do the same kernel over this block. Here I write the value. The same way, the multiplying of each row column summing up. Third, I move on here, do the same operation. Here I write the value. I hope you get it. This is my kernel. This is my input image. This is the feature that I extract from this kernel. Agreed? And this operation, we call it as convolution of this kernel over the image, over the input. Right? This is the first step. What we do, we can get out Salient features as we wish. Now consider one small thing. Suppose, so when we extract out, suppose we, so just look at the X example because it is easy to make you understand. Suppose I scan this cell. If I scan this cell, what will be my output? See, 1, 1, 1, 1, 1, and then 4 -1s. All of them are -1s. So this will be some negative value of 2 if I scan this cell. Right? Or rather negative of 1. So you see that this cell doesn't matter in center finding. This particular block of convolutional answer doesn't matter in center finding. So what I will do, so therefore you can see such kind of a feature when you extract out by convolution, there will be some value which is significantly higher. There will be some value which may be significantly lesser or lower. Right. Now what I will do, see, the whole job of building such kind of a kernel is to take out the prominent features. So I will just eliminate this insignificant thing and make it 0. Let me give you a very practical example. Suppose from an image you are trying to detect the edges. So wherever your kernel doesn't find an edge, this value will be significantly lesser, rather than where it finds an edge, this feature extracted value will be significantly higher. So if you only want edge to be extracted, why bother about the rest less significant value? What you do, then each of the pixel, you either take max or the value that you get. Either take 0 or the value that you get and take a max of that. This operation is called rectified linear unit. So first you do convolution, then you pass through rectified linear unit to make your features prominent. Right? I hope you can understand what do we mean by prominence here. Yes or no?
Prominence means age, prominent.
No. Edge is an example. I am saying that, see, what is the goal of a kernel? This goal of this kernel is to find the center. So
Yes.
wherever there is not a center, it's a drastically less value than this. So I do not
Yes.
bother wherever that is not a center. So suppose I got a center only here, the rest I can just eliminate as these are not dictating anything. So instead of not only passing through a convolutional net, this kernel and convolution value, if I just pass it after that with a rectified linear unit, then I can get absolutely my features which are absolutely prominent.
Oh, yes, sir. I got it.
That's the overall. So where we are, suppose, let me again try with my artwork. Suppose we are trying to locate a car. Now, what we are doing, we are extracting out such kind of things. Piece by piece, but also there could be overlaps. I mean, it's not always piece by piece. Then what we are doing, we are passing it and extracting a feature box, small feature box from every of them. And this is convolutional plus after rectification. Remember that we could have such things multiple times. Even with all of these, I could look at these and can take out a feature. I could look at these three and take out one another feature and can move on like this. So there could be multiple convolutional plus rectified linear unit layers. What does this signify? Suppose this has detected the edge of your car. This through the edge will detect the object, meaning where is window, wheel, these are the objects. Here, the associations, that wheel is at the bottom, of this is at the top, you may, and go on doing and extracting out the features with this, as many as you want. The only difference that we make as per our knowledge in artificial neural network is that we went deeper to extract more features, F1, F2, F3 hierarchically, and compose them. And also at times we went more broader, right? Because the more different things that we would like to foresee and compose is the breadth of each layer that we should went into. We have went into. And finally, what if you have understood the associations and could find out the objects, because at the final layer, you have to say it is a car, it is a bus, it is a truck. This is the final layer. So somewhere getting out all these features a feature map, finally, what you do, you have to flatten out these features. So you have done convolutional, then rectified it, taking a max, pulled the value, and then finally you need to flatten it, and you will flatten and pass it through a fully connected layer at the final, fully connected layer to dictate the possible outcomes. This is the final part that we add on to this convolutional neural network. So this convolution and ReLU, this rectified linear unit, as you can see, we just go on with the ReLU by pulling the values. In the previous case, like X finding and the edge finding, we did a max pulling because the significant areas are of importance. So we are pulling it the maximum values. The rest we do not care. We may pull the maximum significant values only. However, if we could see the intensity, the symmetry, all these things, you can see the max pulling will may not affect. We may also go for average pulling because suppose a feature is such that you need to see the symmetry of that number, the intensity of the pixels. So the intensity is not the maximum thing we will keep, the rest we will dictate, we will throw away. We will just try to keep an average. So depending on the context where you need to learn, whether you select pulling as the, that means the feature tuning as max pulling or average pulling, that is dependent on the scenario that you are applying this convolution. But finally, when you get it these features, now you need to flatten, meaning that this compressed feature map need to take out certain values and weight them to dictate that is a car or a bus or a truck. Suppose, how does we flatten and then can get a decision? For cars, usually the size will be less. Some feature has dictated me what is the size, the length of the car. The bus, for bus, the length will be more. So the weight on the size here, the weight on the size will be also a dictating parameter to learn in terms of giving a vehicle or classifying a vehicle as a bus or a car. Truck, this portion, the size of the back portion is also a factor. So this is from the feature what we identify as an object, as an association. How do we flatten and disseminate this knowledge in terms of the weighted values and can compose them to classify finally? So this is the final part of it, is obviously the classification, the traditional classification part by ANNs. That's why we just flatten and make a fully connected layer. Right? So this is what the convolutional neural network architecture is all about. Now the question is that how can we select kernels? You said very well. I mean, you just take out these things, build a feature map, but I need to know what I am looking into. How can I know that which is my best kernel? How can I know that? And also, how can I know these weights? You already know the answer. How will you do that? We have images to train. So at each of these layer, earlier in artificial neural network, you are training at each layer what? The weights, remember? At each layer, you are training the weights. Along with that, you will also train what will be the value of a kernel. What will be the value of the index of the kernel. So this is your training. Now see why we need huge amount of training data to make it better. Because unless you have a huge amount of training data, all of them, these parameters are open parameters. In artificial neural network, they are more than that, because now not only you have weights to take it forward, also you have the feature maps to find into from kernels. So each of the kernel entry also has to be found out by training. Therefore, this can only be applied if we have high amount of training examples. This thing is very actively we can deploy, right? And easily you can see that my kernels could the choice of kernels could dictate whether I want to smoothen an image, whether I want to sharpen an image. So all of these are image theoretic operations in image processing. So accordingly, my kernel will get multiplied or will get convoluted with the image and can make it sharp, make it smooth, detect the boundaries, that is detect edges, and all these things we can do. But where do we lost? Do you know? I mean, where we I mean, where we made kind of a demeriting aspect here. Can you tell me what is the demerit in such kind of a deep, broad convolutional neural network or any kind of a deep networks?
Time consuming, training time high.
One is the training time consuming. Training time is huge. Second thing, you need this, otherwise you cannot do good. High amount of training example. But third thing, see, you absolutely lost the explainability aspect, isn't it? Because look at this one. I got a value. I mean, it's the center because I know I tried to design a kernel. This is a pathological example, but in a big crowded, say, road, you are dictating whether a pedestrian is moving, a car is moving, which side it is moving, traffic light is red, all of them composed together, and you are saying that there is not an accident, right? So see, looking at an image, suppose I'm predicting there is not an accident in this road. What you are doing? Where is the pedestrians? Are they crossing? Are the car moving? What is the traffic light? All of them gets composed, and move forward, feature extracted. Finally, I find it. No, there is not an accident. So we completely lost the explainability aspects when we go on keeping pooling and all these things, several ReLUs and convolution network, flatten it out, and then finally make a decision. So that's an inherent research challenge that people are also trying to address nowadays. That how can we make my network more explainable, right? Because not only this case, because convolutional neural network is also used, one of the most successful use case or the application of this is in medical domain, and it has been very successful in breast cancer detection. One of the famous thing that happened through convolutional neural networks is breast cancer detection. It's pretty much successful over that. Well, looking at the image, it detects the cancer cells, the cells are cancerous or not. So all these things can happen. So when you do that, I mean, you cannot tell the patients that your theta value, lambda value, and your mu value is more than 0.5, so you have a cancer. I mean, that's not a big. I mean, that's very problematic, because if I say that your lambda value is more than 0.5, so you got a cancer. So we need more explainability features over it, and people are having a deep dive into research for these issues. So this is in a nutshell two things we tried to cover up. One is that going deep, going wide. What does deep neural network mean? And the recent boom of neural network is primarily to this. I mean, I will encourage you just to look at ImageNet. There is a data set called ImageNet. Whenever you get time, maybe in the summer vacation or sometime, you just take that data set and try to build a convolutional neural network with this, and try to see that which feature that it can tell. Can it identify object or not? It's a fun exercise, because in Python, in PyTorch and TensorFlow, all these things, convolution and ReLU is just a calling of a function, nothing else. So it's easily you can stack over the networks. You can just learn a kernel and can detect it, and it's a very pretty good exercise that you can do many things with this deep neural networks, and you can get a feel of deep neural networks. Any questions on this? Okay. Neural networks and the proliferation of deep neural networks, as we are talking about, to understand image, has also a side impact. Suddenly, the field of transfer learning makes a huge roadway, huge pathway. Why I am telling? What has happened that suppose, and first of all, what does transfer learning mean? What is a transfer in learning? So transferring learning means, let me give an example. Suppose I develop a CNN which can recognize objects. whether it's a ball, whether it's the cat, such kind of objects it can recognize and learn and recognize. Now, can I use this to recognize, let's say, X-rays? Suppose a hand is broken, particularly bone is broken or not. See, two things to notice here. One is that obviously the learning aspect, that the thing that we learn here, that particular model that we learn, we will transfer it here to recognize this. So in a way, your learning get transferred from one domain to other. Maybe it's a restricted domain than this, but I will tell you when to apply it and when not to apply it. But we can, it's a transfer of whatever you learn and get a model. Can you use that model to again do this same thing, similar types of things, but in a different context? You have not learned to see the X-ray scans and detect a bone is broke. You have learned to see the object and detect whether it's a cat or a dog. So the basic philosophy is like this. I mean, since we are at the end of the course, I am just giving you the philosophy and the process to understand, because the mathematics is deeper. So suppose an image, when you look at an image, as I said, it goes through several kinds of layers, convolution, ReLU, and max pooling, and go, and so on we move. And suppose I get an image, y hat is my predicted value, looking at an image. So this is the model I learned from this. This is the model I learned from the first part. That is, when I try to recognize objects, I train it from ImageNet, and I find that something is a, let's say, the cat. If there are multiple things you need to, I mean, if there are multiple things you have learned, then that is not an issue, because you will have multiple final output layer. This will be y1, y2, multiple features you can learn. Okay, that's not an issue. But to make things more simplified, let us say that we have learned something looking at an object, something is present or not. Now I want to transfer this model directly here. So first of all, I mean, it's not directly applicable. It's input domain only matches. The output domain has different thing to reason about. So what only transformation I will do is that, see, the out to reason an object and to reason the X-ray scan to be something present or not, I need to have a change here. So obviously I will just scrap this one. I will take this and try to build a new layer which predicts, suppose this is y and the X-ray scan is y dash. This is the first thing we do in transfer learning. So then what happens? So this layer has new weights to be learned. All of them are, some weights has been frozen after learning while recognizing the objects. This is a new thing you have done. You have to do it. You have to learn this. So all the existing X-ray scans and levels, suppose I have 1000 X-ray scan and level training examples. I train these networks again and again. I train these networks and then get this WME. So now this could be applied. See, why I thought about transferring the knowledge, because you remember in convolutional neural network building up, what we are doing, we are extracting features. These are my edges. These are my objects, right? We have done it in this way. These are my associations. Now, this is also an image, first of all. Now, all of these may be common features to this image as well. Because this is an image, we need to know the image by seeing this. Now, if you have higher number of training examples here, then you could have also tweaked some of the weight values in between this. Not only this one, you not only learn this weight, but could have also tweaked some of the weights you may refine it. But this is what we mean by transferring the knowledge that you learn is when you build up a model, similar like domains, but a different outcome you need, you may try to transfer the model to that. But you need to be very careful about two things. This model, when you build, the number of training examples to build the first model, I'm saying M1, should be huge. The training examples for the M2, that is after transferring. So this is model M1. I am trying to transfer to M2. This is less, it is okay. That's why you see that we need, let's say, 10 to the power 9 of such thing. I 10 cube of this thing will be okay. Right? So this is a must. This is a must for such kind of a thing. Now, if you have less than that, the thing is that only this weight or some of the adjustment of the weight will matter, but eventually the image, the image identification is still quite good because you have trained it to a different variety of images. The other such thing, the same nature of such thing, you can also see another example if I give you is from the speech domain. So here your model 1, which is the initial model that you could learn, is let's say you want to have speech recognition system to learn from, and you need to transfer this knowledge to have a wake-up call. For example, I'll give you an example of this wake-up call. Suppose you have an Alexa at home. I hope you know what is Alexa is. It's a device which listens to your natural languages and can enact upon by either searching the Google or from its database. It could play a song, it could play, it could give you a meaning of a word. But if you see, how do I say to tell him something? I tell him Alexa. I tell him that, hi, these are my wake up calls of a device. Now see, speech recognition system is more generic, just like we have an image thing, but we need a focused X-ray to we finally do. So usually for speech recognitions, we have, let's say, 10 to the power 5 hours of data to train. However, such wake-up calls, we have only 10 hours of such wake-up calls as a training labeled wake-up calls. So why we do not directly do up a model of M2 directly from this one? Because we have very less data. If we build direct model for this one, this could be quite inaccurate. Instead, we could leverage this one, build this, transfer the knowledge here, retrain it to make it fine-tuned and do it. Agreed. I mean, you may be wondering that why can't we directly do a wake-up call model directly by training? The only problem is that, as I said, this training data is less, this training data is huge. These two activities are somewhat similar. That's why we need to build a model from the higher training data available experience, put that experience, train it, or rather fine-tune it to make this model look good. So we have two stages. The step 1, we sometimes call it as pre-training. Many of you have heard these terms. And step 2, as I already am telling it multiple times, we call it as fine-tuning. So by pre-training, you build a model, you throw it here, delete the last layer, and then by fine-tuning, you do it. Sometimes the final layer, so at the final layer, sometimes instead of one block, we may introduce multiple layers. That's not an issue. But the only consideration you need to make, see, introducing multiple layers, such connections will also introduce newer weights, right? So if you have less amount of training data, the accuracy that you get by introducing new parameters will be lesser. If you have higher training data, then you could go a little bit deeper on that. So it's a trade-off people sometimes try to experiment with and see that what performs well from the cross-validation and all that. But the whole essence is that the final model that you want to get in, you have so less training examples that even if you get a model, it could not be accurate. So why not? I could use some model from a similar kind of a training domain where I have larger set of examples, and that model I could transfer and just make a little bit fine tuning by the weights, maybe the internal weights that the model has learned. By the training example, the meager amount of training example that I have here, and just I do this thing similarly. Right? So it is sensible when you have a lot of data from where you are transforming and you have less data to where it is transforming. but the vice versa is never recommended, because it's I mean, if you directly try to do a model here, you will get inaccurate one. So this is the whole essence of transfer learning. And as you can see, all these convolutional neural networks and all that, if you understand this philosophy, then the similar back propagation, the rectification of weights, all of them, I mean, I could do a hairy mathematics of all this, but I prevented myself to do that, just to give you an essence that why going deep, going wide makes sense. What does we gain and what does we lose in terms of explainability, as I've explained. And here is the research that people are doing, trying to incorporate a little bit of explainability along with this. Any questions? Nothing. I mean, it indicates two things. I mean, rather three things. One is that I explained too well. Two is that I didn't explain at all. And three is that you are all diplomats by now. By the end of the semester, you are all diplomats. Anyway, I mean, if we have, that's all I would like to cover today. We are already 12:55, so I don't want to dive into another new topic. Tomorrow, we will also continue another aspect of deep learning, which is the sequence modeling aspect in terms of a recurrent neural network. So if there are no more questions, we can stop.
Sir.
Yes.
Hello, sir. You said that by convolution we learn that it is a line, then it is a another thing, something. So, sir, how all these things converge at the end? Like how they?
Oh, they converge not at the end drastically. They converge layer by layer hierarchically. See, first you detect an edge, then through an edge you detect an object, then through a set of objects you detect a patch or maybe associations of that, right? And you grow up, finally determining what the object is, right? Just think about the biometric sensing of your face. I mean, if some devices can see your face and can unlock, what does it do? It first senses where is the eye, positioning of eye and ear and nose and everything. Then it tries to relate the features, the gap between the eyes and the nose and the heights. Then it tries to figure out the objects, whether this is X person, Y person, Z person, and then it figure out the traits of it, the color, complexions, and all. So different visionary aspects get converged hierarchically in different layers, finally to flatten out and can say that this is person X, person Y, person Z, and so on. That's how it happens. And see, Deepak, the main point here is that you do not have to bother how it happens. You only have to lay out a network for that, and then you will train, right? You will give an image where there is a person who is of dark complexion, whose maybe eyebrows are very thin. You give an image who is a bright complexion person whose eyebrows are thick. Many things. We have mustaches, who don't have mustaches and all. So all of them gradually incorporated in the network, train the network, the kernel weight, the weights of the convolutional, the layer to layer weights, and then they fine tune gradually and finally make a model so that any new image you give, according to that, it will dictate. So it's an experience it gathers and builds up.
Yes, sir. So actually, sir, I am trying to visualize how one line, then something, then box, then
Oh,
this kind. So
you like to see you like to see that? Just give me a minute. I'm just stopping the sharing. Just wait a minute. I'll show you one thing that will clarify what does it mean. Just a minute. I have it anyway. Okay, look at this. Are you able to see this?
yes, sir.
Yeah. Now see here. Suppose I was just looking into a face, right? I mean, just like this. I mean, here. I hope. Do you know her name? I mean, this lady. It's a very famous lady. Comes from the image processing book. I mean, the image processing book claims it. Her name is Elena. Suppose I want to just identify that this image. So see, what I will do first is that I will see edges, dark spots. These are low-level features. Mid-level features, you can see now the eyes, ears, nose, these things are coming up, right? And each of these boxes, you may think of an output of a particular neuron node. Then you compose for the high-level features where you compose eyes with nose, make an association. This is the head side, this is the chin side and all that. Then you go on and do that. So in between, if you try to visualize what is happening in between exactly in each node output, this you will see. If you try to reconstruct the image after each neuron it passes, you will see such kind of a thing. Agreed? This is what you want to ask.
Yes. Yes.
Yeah. And the problem that I have already mentioned to you is this one. Suppose your image could be tilted, your image could be illuminated in a different way, your image could be scale-wise different. There could be background clutter, camouflaging. There could be variations in the chairs that you can see. There could be occlusion. Now, all of them you can only extract. If you could extract features, combine them gradually, you can build up. That's what I was saying.
Yes, sir.
It's a fun. That's why I told in summer vacation, please try to go with the ImageNet and implement one convolutional neural network. Okay, any other questions? All right, so that's
Suppose,
it
sir,
from, yeah.
suppose for I want to make a model for time series data. So, sir, how
Okay.
I will think like which layer
Okay.
to add, where to add, like how I will get this intuition, like
No, suppose
how.
in time series data, see, I mean, why, first of all, why do you want to make a convolutional model? Time series data, tomorrow recurrent neural network, which model sequences is much better. Anyway, if you want to have a convolutional neural network, what you want to do is that the relation, you need to first look into the relations of it. See, a human face, I want to find out the eyes, the edges, the ears, the eyebrows, the chins and all that, then association. So in time series data, you must have a knowledge what you want to do at the end. I mean, what you want to classify. Start from there. Try to figure out the low-level features, mid-level features, high-level features. Try to develop such layers. Experiment over the depth and breadth of the layer. Experimenting means give the input, the training examples, keep on experimenting it and cross-validate it. You will finally find out that there is a certain composition of it that keeps it. Now, you cannot reason out right now with this because all of them are garbled up in between. That's what I said. We lost explainability due to this. Okay, but you can guess something and can train it and can have a network that enforces your guess. That's how it works.
Okay, sir.
Okay, so I mean, if you're interested, there is a course in deep learning. I hope in the project they give such kind of activity as well. You may think of taking it in the next sem or whenever it is. Okay. All right.